The focus of this video will be on influential points and coefficients of determination. But before I talk about those topics, I want to bring up a couple of other very important points that always need to be considered whenever working with a linear model. And the first is that you should never extrapolate. Extrapolating refers to making predictions outside of your range of data. So if you think back to the example where we looked at the relationship between price and square feet of homes, the homes that we were working with were between, I want to say, 2,000 and 3,000 square feet. And so the model that we created was specific to homes in that kind of a range. If you tried to predict the average price of a home that was maybe 4,000 or 5,000 square feet, and you were going to use the same model, then you would be doing what we call extrapolating. And this could lead to some very unreliable results. So do not extrapolate. And then the other main point right now, you should know that correlation is not the same as causation. And maybe you've heard this before. These terms often get misconstrued, and it unfortunately leads to some miscommunication and many misunderstandings. But you should know that the associations that we're capturing in a linear regression are strictly that. They are associations. And you should not confuse that with one variable causing the other. I also want to tell you that it's very difficult, even from a statistical standpoint, to prove that one variable is causing the other. And so, again, our emphasis here is on associations or correlations and not one variable causing the other. Okay, now let's talk about influential points. And to talk about influential points, we're going to be going through this example. And I should begin by saying that an influential point is kind of like an outlier with bivariate data. And it's a point that, when included in a scatter plot, strongly impacts the position of this least squares regression line. And as you're going to see in this example, when a scatter plot contains these types of points, it's recommended that you compute the regression line both with and without the outlier to determine if the outlier is influential or not. Okay, so I've taken this data in this X list and Y list, and you can see that I've entered it into L1 and L2. And so the very first thing that we're going to do is look at this in a scatter plot. So I'm going to say second Y equals, make sure my plot 1 is on. It is. The scatter plot is selected. My X list is L1, my Y list is L2. I can now press zoom number 9, and it gives me a nice scatter plot of my data. A quick glance at this scatter plot reveals that we do have this point that appears to be an outlier in that upper left quadrant of our graph. And we'll deal with that in just a second. But right now, let's compute the least squares regression line for this particular scatter plot. And so I'm going to press Stat, go over to Calc, and I'm going down to number 8, and number 8 is linreg. My X list is L1, my Y list is L2. And I'm going to store the regression equation into y1. So I press vars, yvars, function y1, and then we can go down and press calculate. And when we press calculate, we get the following regression line. So I'm going to write this over here. I've got y equals 8.9888, and that's if I'm rounding to 4 decimal places, plus my b value times x, so plus a negative 0.9703x, again rounding to 4 decimal places. Okay, let's take a quick look at what this graph looks like of the line of best fit with that outlier present. So I just press the graph button, and once again we can see that that outlier in that upper left quadrant is probably influencing this a little bit, and we're going to be able to clearly see that now by removing that outlier. So let's look at our table of points and figure out what point from this table coincides with that outlier that we're seeing in the graph. And I think with a quick glance we can look at this and we can see that the ordered pair that really kind of sticks out is this one right here, this 1.8, 9.2. Remember that outliers are always ordered pairs, so it's an X and a Y that go together. And so our outlier in this case, 1.8, 9.2. We're now going to remove that outlier and recompute the least squares regression line. So I'm going to go into Stat Edit, and I'm going to identify where 1.8 and 9.2 are, and I'm going to press the delete button. on each of those. And now we're going to press Stat Calc. Let's go back to number 8, linreg. And this time we're going to store the regression equation into y2 because we want to be able to have both of the regression lines in there. So we're going to press vars, yvars, function y2, and then press calculate. And my new regression line is the following. Now I have y is equal to 5.2915 plus a negative 0.1413x. And so even if we just compare our original line to this new line from a numerical standpoint, so we're just looking at like our y-intercepts and our slopes, we can see that things have changed quite a bit. And if I go back to the graph, I have my original regression line in blue, and this new regression line is in red, and the red one does not was formed by not including that outlying point. You could see that things have changed quite a bit. And so the relationship that we have between the x values and the y values is definitely different now. And as a result, I would say yes, the outlier is influential in this problem. Now, a lot of times students wonder, well, how do you know? Like, is there a cutoff or a threshold? There actually is not. This is very subjective, but most of the time, when you remove an outlier, it will impact the shape of your regression line. And as long as it's more than a very small change, then we're going to say that the outlier is influential in this class. Okay, let's take a look at one final topic, and that's called the coefficient of determination. Now, the coefficient of determination is much like the correlation coefficient that we saw earlier in the class. So remember that the correlation coefficient was used to kind of determine the strength of a linear relationship. And that's really the exact same type of thing that we're going to be doing with the coefficient of determination, r squared, as well. The difference is when we're dealing with r squared, we can actually interpret the number as a percentage. So r squared, the coefficient of determination, has a little bit more mathematical meaning or a little bit more mathematical interpretation than r. So we describe r squared by saying it gives the percentage or the proportion of the outcome variable that's explained by the regression line. Or in other words, r squared is the proportion of the variation in the outcome variable that is attributed to the predictor variable x. So let's take a look at these three graphs right now and see if I can give you a better idea of what I'm talking about. If you take a look at this first picture, you can see that all of the points are falling perfectly on that regression line. So in this case, the regression line is perfect at capturing the variation in the outcome variable. So the percentage of the variation in the outcome variable that's explained by the least squares regression line here is 100%. And that's why we would say in a case like this that r squared is equal to 1. But in a picture like in the middle, the points are not all perfectly on the line, but they're pretty close to the line. So we would say in a case like this that the least squares regression line is capturing a large proportion of the variation in that outcome variable, but it's not going to be perfect. So r squared won't be equal to 1, but it is going to be close to 1. And then in the last picture, we can see that the regression line actually does a really poor job of kind of predicting what's going to happen with the outcome variable. And therefore, the proportion of the variation in the outcome variable that's explained by the least squares regression line is really low. It would be much closer to 0 in a case like this, much closer to 0%. It would probably still be some small positive percent, but definitely be closer to 0. Okay, so let's wrap up with this example right here. The correlation between size and selling price of homes in the Denver suburb from the beginning of this module was R equals 0.9005918. And so we can compute the coefficient of determination. Now typically you're going to have that coefficient of determination right away as soon as you get R when you do the linear regression, because the calculator will give you both R and R squared at the same time. But in a case where you simply have the correlation coefficient like right here, to figure out that coefficient of determination, all you need to do is take that R value and square it. So let's take 0.9005918, square it, and we can see that our coefficient of determination is 0.8111, and that's going to 4 decimal places. So what that means is exactly what the next question is getting at. The coefficient of determination tells you how much of the variation in the outcome variable is explained by the regression line or is attributed to the predictor variable. And so in the context of the example with the size and the price of the homes, we are saying that 81.11% of the variation in the selling price is explained by the square footage. So that is how we are going to be interpreting this coefficient of determination. You just take that number and you rewrite it as a percent. And then that means that 81% of the variation in the outcome variable is attributed to our regression line or is attributed to the predictor variable from our regression line. So if 81% of the variation in selling price is attributed to square footage, then doesn't that mean that there's another 19%, approximately 19% of the variation in selling price that's going to be explained by some other factors that are not seen here? So there's other variables involved that we just are not familiar with at the moment. Okay, now I should also tell you that while I'm kind of giving you this overview of coefficient of determination, the textbook goes through a really nice explanation of the mathematics behind the definition. So if you're interested in the math behind the scenes here, I strongly encourage you to go check this out in your textbook. And then also be sure to check out the next video where I'll go into just a summary of everything that we really talked about in this module. Thanks a lot.